And so hello, welcome back, YouTubers. We're going to talk about our kOmega model, kOmegaSST model, and see how these functions actually change with distance y from, let's say, the wall. Okay, so that being said, we just continue, right? We'll continue to go forward. Okay, so the next step is let's see, we are talking about near wall behavior, and we wanted to look at some wall function. So yeah, we want to find out how this k and this omega actually vary with y plus, so that we can see how these blending functions like f1 actually vary apart from the wall. So the key thing I want you to know is this thing called, the key document is called Near Wall Behavior of Reynolds Average Navier-Stokes Turbulence Models and Implication for Wall Functions. So from there, oh, this is the wrong one. Yeah, you go to Google Scholar, you search this, you have this, and yeah, if not, you'll have this from Sightseer, from, I think it looks like Penn State. Okay, whatever. psu.edu. It's supposed to download, and there you go. Okay. So this paper is from Stanford. Okay, so we go straight to the important juicy bits. Juicy bits are over here. Okay. So in the kOmega model, it says in the viscous sublayer, the equations of the kOmega model reduce to like this. So what is this actually? And okay, so we have simplified the equations in the viscous sublayer. For example, the standard kOmega model equations reduce to this. So what's all this over here? So let's take a look. So let's take a look at the kOmega model, or kOmegaSST. Over here will be the turbulent kinetic energy equations. So yeah, we have this k equation, alright, which I'm going to just write down, or rather I just copy and paste from what we have the last time. Okay, so we have this. Okay, how did this k equation come about? So we have this, alright, then we start non-dimensionalizing it. Okay, how do we non-dimensionalize? We refer here, I think in the earlier part, we'll have k plus over here. So k plus is k over u tau squared. Over here, this is how we non-dimensionalize near the wall layer. So k plus equals to k divided by u tau squared, or u star squared. This is the friction velocity. Okay, so this is the friction velocity, where tau, or rather u star, okay, I like to call it u star, equals to square root of tau wall divided by rho under the constant wall shear stress assumption, or constant shear stress assumption. Okay, so this is the friction velocity, and yeah, how, and then okay, omega is non-dimensionalized in this way. So omega plus equals to omega into nu over u tau squared. So that's how we non-dimensionalize omega. Omega nu divided by u tau, or u star squared. Okay. So that's how we non-dimensionalize. The rest are more or less the same. We'll just leave it be. Okay, so you just want to non-dimensionalize the k and omega. So this is I mean, for incompressible equations, this is pretty much, yeah, u star is pretty much constant. So we can substitute k equals to k plus u star squared. So I'm just going to quickly go through concepts. I'm not going to go through the whole thing, but okay, I'll just do this first. Alright, u star squared over here. Alright, this one should be, yeah, since this is a constant, we just bring that part out. Okay, and then here also we convert this into a plus, and u star out here, u star square out here, and we have a omega and k over here. Yeah, because this is just epsilon, so I just copy and paste. We'll do the non-dimensionalization as follows, and just paste this here. Okay, paste this here, and then omega will be omega equals to u star omega plus into u star squared over nu. Omega plus u star squared divided by nu, and that's just rearranging this equation here. You bring this to the other side and divide both sides by the kinematic viscosity. So just copy and paste here, and that is done. So there you go. Okay, so let's just combine the terms here. Okay, to the 4th power, I'll get rid of this. Okay, and there we go. Yeah, so we divide throughout by the friction velocity squared. So I just divide throughout as follows. Okay, and we apply the boundary layer assumptions, but I think before that there's also this uj which we want to non-dimensionalize. So uj equals to u plus u star. Okay, but we find that all of this is not going to become very important because the convection terms are going to be small in the boundary layer. So in boundary layer, we assume a few terms will start disappearing at a snap of a yep. All of this is 0. Okay, production term is also approximately 0. Okay, this one is a standard boundary layer kind of assumption, I think. I'm not going to explain why, but in boundary layers we like to cancel lots of terms out. So yeah, so this is a steady state and all of this as well. This approximately 0 in a boundary layer, the production of turbulent KE is negligible. More so in the viscous sublayer region. Okay, so we get this, and then so we get this equals to 0, and this is all we are left with. Okay, so I can divide both sides by this this nu, and we will just get 1 as nu t over nu, standard equations. Okay, and there's this constant sigma k omega SST. Okay, so and I want to also do this non-dimensionalization. In boundary layer, we only consider y direction, so we simplify. Okay, y here, and then we non-dimensionalize as such. Y equals to, okay, y equals to y plus nu divide by the friction velocity u star. Okay, so we have 2 times of that happening. So I'll get this out here, 1 and 2, and then I'll bring a u star out, and divide by nu squared on the outside. Okay, so I'm doing this because I'm just changing this variable here and this one here also. Okay, so I'll copy and paste this here because I brought it out. And yeah, we are almost there. Did we divide throughout? Where did this come from? Oh yeah. So I should have a square here if I divide throughout. Okay. Alright, so anyway, yep. And yeah, that's right. So I just multiply throughout by this term here, so I get rid of this. I mean, I divide throughout by this term, and I'll get this answer here. Okay, and yeah, so we're almost there. In the viscous sublayer, we assume nu t is much smaller than nu, so we can ignore this second term, and that's how we just get 1 over here. And of course we can just get rid of the 1, and then this is what the term looks like. And yeah, this is what we end up with. Okay, I think I missed out a c mu somewhere. Okay, it looks like I'm missing a c mu somewhere. Okay, but okay, long and short story is that you get the k equation looking something like this. I mean, if you do the same for the omega equation, right? You do the same for the omega equation here. You eliminate most terms like the source term, and you eliminate these 2 terms, and of course the k epsilon term also drops out. Then we are just left with the dissipation term and the diffusion term here. Okay, we do the same boundary layer stuff, and then the differential equation we end up with is this. Okay, I'm not gonna, I think I'm missing a c mu, but maybe I think it depends on how you define this omega plus, right? Because I mean, this is where we find our c mu from. Okay, when beta star equals to c mu, but yeah, if we just substitute this in, we might get our missing c mu from there. All right, and substitute this in, we'll get our c mu. I mean, it's just simple as that. Okay, so I think the definitions can be a bit confusing, but you do the same thing and you'll get this. All right, important thing is to find how this omega actually changes with y, omega plus and k plus. Yeah, so if we use omega star instead over here, if we use omega star, then your k equation will be as such. Okay, omega star. Okay, So and then you have a C mu in front, C mu. All right, and that's that. This one actually looks more like it's derived from here, and yeah, it's derived from this one where you have a beta star in front and the omega is defined as such. Yeah, so hopefully that clears up some confusion. Yeah, but apparently this one looks like the omega star that this one's using. This one's using omega star rather than omega as we are normally used to from the theoretical derivation. But yeah, this is how we do it. Okay, just so you know, there's a typo. It looks like there's a typo here. Equation 1.20 of this project, the sign of this should be negative because the paper it quoted, it should be negative, and from the paper it quotes from, this paper project actually quotes from, it says that the coefficient of this dissipation term is negative. Okay, so likewise you do the same for here, and for the sake of time I'm not going to I'll skip the omega plus derivation unless it's like really needed, or rather omega star plus derivation. But long and short, after you go through all of these equations and then you solve these ODEs, okay, you start solving these ODEs in the boundary layer, okay. In the viscous sublayer. Okay, I'm not going to go through how we get that. Okay, but I'll just put the solutions here. Okay, because that's more important. Omega star plus equals to 6 divided by beta 1. What is beta 1, by the way? This beta 1 actually corresponds to let's say this beta over here. You see this beta over here from this dissipation rate, and you specifically use the beta because they actually provide two betas for you and two alphas. Okay, one of them, the beta 1 will correspond to the k omega model, beta 2 will correspond to the k epsilon model. So remember in the last few videos we were trying to see the difference between both models. We saw that the experimental coefficients were different, so therefore both of them are provided here. And of course, based on your blending function, like near the wall, you want the coefficients to reflect more of the k omega version rather than the k epsilon version. So you see this blending function also comes into play when you deal with the coefficients as well. But I'll just leave it as that. I'll come back to that later. So this is beta 1, 3/40, which is corresponding to the k omega, the k omega equation. Okay, so okay, let's see. Beta 1 equals to 3/40 k omega equation constant. All right, this is where we get it from. Okay, so y plus squared. All right, so likewise, okay. Anyway, I need to write this down also. Equals to just copy and paste this template. Yeah, this is the ODE we are solving. Omega star squared, and you have a beta and omega squared there. Beta 1 omega plus star plus squared. Okay, omega star plus squared. Alright, so this is very similar. You will see the similar expression over here. Oh, sorry, you see it here. Yep. Alright, so to solve the So after solving the omega equation, you get this in the viscous sublayer. Then we substitute this into the K equation over here, so that we get rid of this omega star. Alright, and solve the ODE here. We get, alright, we'll get this equation here. K plus equals to some constant CK into y plus to the power of 3.23. So K plus equals to CK y plus the power of 3.23. Okay, so I'm not gonna say how the boundary things are done. I'll just provide you the answers. Okay, so we also have a log-law region. Remember, we have a log-law region, and the expression is as follows for omega star plus. I'll just give you the answer straight, okay? Because it's gonna take a lot of time. Square root C mu. Okay, and then that will go into y plus. Alright, so we have omega star plus as a function of y plus, which is exactly what we want. Okay, and then we have k also. K star plus equals to 1 divided by square root C mu. Now this is convenient for us, of course. There's no dependence on y, it's just a constant, which is great. Okay, so yeah, that's the log-law region. Of course, in CFD code, we have a blend between, you kind of blend between these two functions. Okay, all right. In case you're wondering what the CK is over here. This is from the diffusive flux over here. This is CK. All right. Okay, so CK is this thing over here. Okay, I think I better. Yeah, this is CK. Yeah, I'll kind of discuss what CK is in later on. So at least we have it in terms of some concrete numbers. But for the time being, I'll just stop the video here so that we can continue the next one and this doesn't drag too long. Thanks for watching. I'll see you guys again. Bye bye.